In the magical world of chemistry, where invisible forces hold the universe together, chemical bonds stand as mighty threads weaving the fabric of matter. Imagine a world where atoms, the tiny building blocks of everything, dance around in a cosmic ballet. To keep this dance from turning into chaos, atoms form bonds, connections that bring stability and order. These bonds are not just essential for the existence of life. They are the reason why substances have specific properties and behaviors. Picture this as atoms trying to fill their dance cards completely, hence achieving harmony and peace. The main types of chemical bonds, ionic, covalent, metallic, and hydrogen, each have unique characteristics that make them special. They are like different dance styles in a grand ballroom, each with its own rhythm and rules. Understanding these bonds is not just about delving into chemistry, it's about grasping the principles that govern the tangible world around us. By exploring these bonds, we embark on a journey to appreciate the elegance and simplicity of nature's architecture. So, let's embark on this scientific adventure and uncover the magic of chemical bonds. Ionic bonds arise from a beautiful exchange, much like a gift-giving ceremony between atoms. One atom donates an electron to another, forming charged particles called ions. It's like giving away a spare book, creating a bond of friendship. A classic example is sodium chloride or table salt. Sodium donates its extra electron to chlorine. This turns sodium into Na+ and chlorine into Cl8. The attraction between these ions creates a strong ionic bond. Ionic bonds are crucial in many minerals and compounds. From salt in our meals to minerals in buildings, these bonds show the power of electron exchange. Beyond the science labs, ionic bonds shape the world in fascinating ways. Take, for instance, the stalactites and stalagmites in caves. These enchanting formations are born from the slow deposition of calcium carbonate, an ionic compound. Water trickling through limestone dissolves calcium ions, which later deposit as these stunning speleothems. In the world of healthcare, ionic compounds like potassium chloride play a critical role. Used in electrolyte solutions, potassium chloride helps maintain heart rhythm and muscle function. This compound's ionic bonds ensure that potassium and chloride ions are readily available, demonstrating how chemistry supports life and health in subtle yet profound ways. Agriculture, too, leans heavily on ionic compounds. Fertilizers like ammonium nitrate provide essential nutrients to plants. The ionic bonds in these compounds make them soluble in water, allowing plants to absorb the nutrients they need to grow. Through these examples, one can appreciate the omnipresence of ionic bonds. Covalent bonds are the epitome of sharing in the atomic realm, where two or more atoms come together to share electrons. Imagine them as close friends deciding to split their resources equally to achieve a common goal. This sharing creates a bond that holds them together in a stable, balanced state. Covalent bonds are the glue that forms the molecules making up everything from the simplest gases to complex organic structures. A quintessential example of covalent bonding is the hydrogen molecule H2, where two hydrogen atoms share a pair of electrons. This simple yet profound act of sharing results in a stable molecule, demonstrating the elegant simplicity of covalent bonds. Another fascinating example is methane, CH4, a molecule where carbon shares its electrons with four hydrogen atoms. This bond creates one of the simplest organic compounds, playing a crucial role as a primary component of natural gas. Covalent bonds are vital in forming complex structures from DNA strands to proteins, defining the architecture of life. Through claymation, this dance becomes a vibrant visual symphony, making the complex choreography of sharing comprehensible and engaging. Covalent bonds are at the heart of many fascinating stories in both nature and technology. Consider the resilience of diamond, one of the hardest substances known to man. Diamonds are formed entirely from carbon atoms, each connected to four others through strong covalent bonds. This network of bonds results in a crystal lattice that gives diamonds their unparalleled hardness and brilliance, making them highly prized in both jewelry and industrial applications. In the realm of technology, silicon, a close cousin of carbon, plays a pivotal role in the electronics industry. Silicon atoms bond covalently to form semiconductors, the foundation of modern electronics. These bonds allow for precise control of electrical currents, enabling the development of computers, smartphones, and a myriad of other devices. Nature provides a stunning example of covalent bonds in the form of cellulose, the primary component of plant cell walls. Cellulose consists of long chains of glucose molecules bonded covalently, providing structural strength to plants. This natural architecture allows trees to stand tall and provides the raw material for paper, textiles, and biofuels, illustrating the versatile and essential nature of covalent bonds. Through these tangible examples, covalent bonds reveal their significance in both natural ecosystems and human innovation. Metallic bonds are the enigmatic forces that give metals their characteristic properties: strength, malleability, and conductivity. Imagine a bustling city where electrons move freely like people in an open market. In this scenario, metal atoms release their outer electrons, creating a communal electron sea that flows around positively charged ions. This sea of electrons binds the metal atoms together, allowing them to slide past each other while maintaining a structured whole. Iron, a cornerstone of modern infrastructure, exemplifies metallic bonding. In iron, each atom shares its electrons with a communal electron pool, creating a bond that imparts both strength and flexibility. This metallic bond is why iron and its alloys like steel are the backbone of buildings, bridges, and vehicles, enduring immense stress without breaking. Copper, another metal with distinct metallic bonds, is revered for its electrical conductivity. The free-flowing electrons in copper allow electricity to travel with minimal resistance, making it ideal for electrical wiring and circuitry. Through claymation, one can visualize the dynamic electron sea, transforming abstract concepts into an engaging story of movement and connectivity. Metallic bonds play a crucial role in everyday life, often without us realizing it. Consider the coins jangling in your pocket. They are made from metals like nickel and copper, whose metallic bonds provide durability and resistance to wear. These bonds ensure that coins withstand the rigors of daily transactions, maintaining their integrity over time. In the automotive industry, metallic bonds are the unsung heroes behind the strength and safety of vehicles. The steel frames of cars are possible due to iron's metallic bonds, which confer both rigidity and the ability to absorb impact. This unique combination is crucial in protecting passengers during collisions, showcasing the life-saving potential of these bonds. Even the kitchen, a hub of daily activity, benefits from metallic bonds. Stainless steel cookware, known for its durability and heat conduction, owes its properties to the metallic bonds within its iron and chromium composition. By examining these real-world applications, we gain a deeper appreciation for the role of metallic bonds. Through engaging claymation, the abstract concept of metallic bonding becomes a compelling narrative of strength, flexibility, and utility. Hydrogen bonds are the unsung heroes in the world of chemistry, often overshadowed by their stronger counterparts yet crucial in their own right. These bonds occur when a hydrogen atom, covalently bonded to a more electronegative atom like oxygen or nitrogen, experiences an attraction to another electronegative atom. Think of them as the gentle handshakes between molecules, subtle yet significant. Water, the elixir of life, is a prime example of hydrogen bonding. The bonds between water molecules are responsible for its unique properties, such as surface tension, boiling point, and solvent capabilities. Without hydrogen bonds, water would not support life as we know it, demonstrating their critical role in sustaining ecosystems. Another fascinating example is DNA, the blueprint of life. The hydrogen bonds between nucleotide pairs in the DNA double helix hold the genetic code together while allowing for replication and transcription. Hydrogen bonds also play a key role in the structure of proteins, affecting their shape and function. Through claymation, the concept of hydrogen bonding can be brought to life, illustrating how these gentle giants quietly underpin the mechanisms of life itself. As our journey through the world of chemical bonds concludes, we appreciate these invisible forces shaping our world. From ionic bonds in minerals to covalent bonds in life's molecules, each bond tells a story of connection. Metallic bonds provide strength and flexibility, while hydrogen bonds are essential in life's complexity. Chemical bonds are the essence of matter and life. They teach us about balance, cooperation, and the dance of particles. Understanding these bonds reveals the principles governing the universe. The world of chemistry is vast and full of wonders. Embracing chemical bonds opens doors to endless possibilities. Continue your exploration and seek the hidden connections that bind the universe. Let this essay be the start of your journey into the captivating world of chemistry.